All right, folks, let's do this. Now, you thought that maybe I wasn't going to do a proof example as one of your example problems, but here I am. I'm doing it. You only have two proofs on the homework tonight. Yeah, right. Only two proofs. You got a lot of other problems. It's probably going to take you a while on the other problems. Anyways, I think this is the harder of the two proofs, but let's take a look at it as an example. Okay, again, before I even read the freaking problem, I draw the diagram out. QYT I'm dealing with, okay? So I got some interior things. So what am I thinking about? This problem is going to have to do maybe with some theorems we've learned. This is probably a parallelogram. Yes, it is a parallelogram. That means parallelogram right there, the symbol. That quadrilateral is a parallelogram, okay, that's given to us. But we're probably talking about diagonals, right? Diagonals of a parallelogram. So now you're thinking, think back to the lesson. What do, right? So work backwards, like predict, right? When you're doing proof, try to predict maybe you're going to have to pull into it. What you know that you might have to pull into it. One thing is that the diagonals of a parallelogram do what to one another? What's that theorem? Scroll up to the section 4.1 to see if there's a theorem that has to do with diagonals of a parallelogram. They do what? They bisect each other, right? They bisect each other. Try to get that memorized, try to get that down so you can pull it out strategically at the right time to help you out. Okay, diagonals of a parallelogram bisect each other. I mean, we know that opposite sides are congruent as well. That's another theorem. That might be something we're going to use. We're probably going to prove congruent triangles at some point in time. That's my guess. Okay, so then the question is, what is it I'm trying to prove? I'm trying to prove that OX and OY are congruent to one another. Those segments are right here. And wait, OX and OY, that doesn't make sense. This and this? Oh, that's it. I wrote QY right there. That doesn't make sense. Okay, right here and right here. So are those diagonals? No, those don't meet the definition of diagonals because diagonals are this right there. There is a bisected diagonal, okay? So we know that TO is congruent to OR, right? We know that. Perhaps you're going to mark that down because the diagonals of a parallelogram bisect each other. There's the other diagonal. There's the diagonal here. So this is just concurrent, right? The segment YX is concurrent with the two diagonals right there at that point. But anyway, so we know that. What else do we know? Well, a little hint. I think we know that. Right? When do we know that? Well, it's a parallelogram after all. Something where is a definition of parallelogram at that point in time. So this is where I'd really mark down to see if you can see it, right? See if you can see it. So here I have an angle, a side, and a side. And then what else is there? Little hint. Vertical angles are congruent. Do you see it? Okay, do you see it now? If you see it now, I just gave the proof to you. Mind blown. Thank you, Mr. Ford. I'm done now with my homework. I can now rest in peace. But if you don't see it, we'll go through it step by step, okay? We'll go through it step by step. Let me get rid of this here. So we have this here to get started, okay? This is our goal. Maybe I'll keep that. I'm trying to show that this isn't, I'll put a question mark down there. We don't know this yet. This is what we're trying to prove. Is OY congruent to OX? That's my goal. And we will try to say it right now. You might be totally confused, and that's okay, based upon what I just drew when I was like, hey, we got it. We'll go through it step by step, okay? Sound good? Let's do it. All right, so we got here statements, and we got here reasons. All right, you can try to write a paragraph proof if you saw it and just want to write about it. If not, sometimes it's easier. It's more structured to write the statements and reasons, okay? So let's start with this here. We have RSTQ is a parallelogram, which is how I translate that symbol to. That's a given premise. And okay, I'm trying to get, so here I'm thinking about what it is I'm trying to prove. I'm going to work backwards where this is what I have here. I'm maybe going to find some triangles that I think I might be able to prove are congruent, okay? There are a few triangles you could try here. Maybe I'll use these triangles here, this triangle here, YOQ and OXS. I'll think about proving those congruent. That just gives me more space to maybe show it to you guys here because I would know if these are the triangles I'm trying to prove. So I think I can prove that triangle congruent to this triangle. And if I did, right, we're just coming out from section 3.7. If I did prove that triangle congruent to that triangle, why would I know that OX is congruent to OY? Why? This is where I ask the class and we all see together, right? Well, I know they're congruent by CPCTC. So if I can get that triangle congruent to that triangle, one more step, OX, segment OX is congruent to segment OY by corresponding parts of congruent triangles. We know they're congruent, and that's what CPCTC stands for. Get triangles congruent, say CP/CTC and say that their corresponding parts are congruent, and then you're good to go, right? You know the proof, and it's going to end with some corresponding parts, okay? What else do I know here? Well, I know, for instance, I perhaps get it out of the way. The thing that's going to really tip me off on this one is that this is a parallelogram after all. Have we used that given premise, okay? So think, you're going to use this given premise somehow. You're giving it a parallelogram. Maybe you can say opposite sides are congruent because it's a parallelogram, but that doesn't really help you, right? Because opposite sides here, QT and RS being congruent, doesn't help you because we're trying to get that triangle congruent to that triangle because that is a side of triangle OYQ. This is a side of triangle OXS. So I'm not going to say that these opposite sides are congruent. I'm going to say the opposite sides are parallel. And you'll see why in a second if you haven't seen yet. Okay, so I'm going to use part of the definition, or I'll use the definition of parallelogram, yeah, but I'm only going to say that these two opposite sides are parallel. QT is parallel to RS, and that is the definition of a parallelogram. And, right, because remember, a parallelogram is simply a quadrilateral whose opposite sides are parallel. That's what a parallelogram is. That's what it's defined as. That's what helps us establish if we knew that something is a parallelogram. Okay, so I'm going to mark those as parallel to each other, right? Just so I know that I've at least identified that in my particular chain of reasoning. Starting from this given premise, I've built onto it. Now, once I said, so proofs can be thought of as a long if-then statement. If RSTQ is a parallelogram, because it's a given premise, then I can say that QT, segment QT, is parallel to segment RS because that's what the definition of parallelogram tells us. But I also, right, you can think of it as if you're writing as a paragraph proof, you can say that, but I also know something else because segment QT is parallel to segment RS. So it's like we start another if statement here. If segment QT is parallel to segment RS, then I'm going to know something else that's going to help me prove that triangle is congruent to that triangle. Why is getting them parallel to each other important, actually? Why did I have to say that? How does it help us? Parallel lines that are cut by a transversal. So let's maybe look at this transversal. Oh, no, maybe not that one. Let's look at this transversal. Oh, interesting. I have a couple of what that angle there and what angle there. What classification do those angles fit? These are alternate interior angles that are formed by parallel lines. Look, QT, segments QT, that line that's on there, that line QT, and line RS, they're parallel to each other. They sure as heck are. And they're cut by this transversal. So a diagonal of a parallelogram is a transversal between two parallel lines. Not four parallel lines, two parallel lines. So this is the transversal we care about on this one here. Or actually, it's technically the transversal too for these parallel lines. But anyways, I'll skip over that. Hopefully it didn't confuse it too much. But we care about these two parallel lines, and we care about this here because this is an alternate. Look, they're alternating sides of the transversal. That's what that's called. It's called a transversal if you haven't been used to using that last semester. So this is a transversal. It cuts across two parallel lines. It cuts across any two coplanar lines, but they just happen to be parallel. If those lines are parallel and alternate interior angles, if two parallel lines are cut by a transversal, then we would know that alternate interior angles are congruent. That's a mathematical fact that we proved earlier on in the textbook. So that is a theorem that you're going to use, my friends, to justify that angle YQS is congruent to angle XSQ, right? XSQ, okay? So I'm going to say that because that adds to my intelligence. I'm gathering intelligence right now. What are some parts, corresponding parts I can get congruent in that triangle versus that triangle? And one is that angle YQO is congruent to angle XSO. And that is because in step 2, if we knew that we had two parallel lines and they're cut by a transversal, we see that in the given diagram right here, then we can make the conclusion, right? Then we can go from this step to this step as we build our chain of reasoning to say that these alternate interior angles are congruent. Okay, so here we just put our justification in words by mentioning that theorem from section 2.2. Yes, 2.2. If two parallel lines are cut by a transversal, then alternate interior angles are congruent to one another. We just justified our statement number 3. Let's move on to statement number 4. So I got an angle congruent to one another. And then we think maybe what's one thing that we also learned this section, other than the fact that a parallelogram has opposite sides that are parallel to one another. When we think back to originally how this problem was constructed for us, this problem has some diagonals that are intersecting one another. QS is a diagonal. RT is a diagonal. And what do we know the diagonals of a parallelogram do to one another? They bisect each other, okay? So what you can say here is, right, because segment RT bisects segment QS, we know that QO is going to have to be congruent to OS because it got bisected by the other diagonal. So we can just simply, in step 4, list out that theorem for us, that the diagonals, right? If we have some diagonals in a parallelogram, they bisect each other. The diagonals of a parallelogram bisect each other. So you don't have to say like that they bisect each other. Like you don't have to say segment RT bisects segments QS. You can just say the consequence of bisecting. Bisecting creates 2 congruent segments, so you can just say that right away. Save yourself some writing out here. Bisect each other. That's what that says. Okay, cool. We're keeping going on. So here we kind of said this is if-then statements. To reiterate what we've done so far. If RSTQ is a parallelogram, then we would know these opposite sides here are parallel to one another. And if those opposite sides are parallel to one another, then we would know that these alternate interior angles were congruent to one another. Okay, cool. So those are a corresponding part of both triangles. If we knew that it's a parallelogram, so here this is where it kind of goes from step 1, right? Step 1 was RSTQ is a parallelogram. If RSTQ is a parallelogram, we can also deduce, right? Also deduce that, I should go backward one step. We would deduce that QO is congruent to segment OS because the diagonals of a parallelogram bisect each other. Okay, so here we're writing this out as a 2-column proof, but you could very easily picture this being a paragraph proof, being a string together kind of if-then statements, right? This here as an if premise gets us to that, but also gets us to that because if we have a parallelogram, we can establish step 2, we can establish step 4. So now we have that. I'm going to mark that up on the diagram. Again, we're working towards getting congruent triangles. This title is chapter 4 is using congruent triangles, right? We want to keep practicing that and flexing our skills there. So here we have this. I'll do 2 tick marks here because I did one with the question mark, one with question mark here, 2 tick marks. So now I have an A here, an A here, and I have an S here and an S here. So now we need to think about what triangle congruency region potentially we're going to use because we got to think backwards. Well, I need to get these triangles congruent to use CPCTC. So now we're going to think I have an A and an S. So is this going to be SAS, right? SAS. And it's not really going to be that. I can't tell YQ is congruent to XS right away because YQ is only part of a side of a parallelogram. XS is only part of a side of a parallelogram. So it's probably not going to be SAS. Is it going to be ASA? Is it going to be ASA? So wait, can I say this? Can I say that that angle is congruent to that angle? Can I do it? Can I do it? And why? And why? Yeah, I can totally do that. So here, what we can say is, well, we have this as our given diagram, and those are vertical angles. You don't need to say that in the proof itself. You can just say, I've spotted this, right? I spy these vertical angles right here, and I know these vertical angles are congruent. So that's a theorem we're going to use next, is vertical angles are congruent. We're going to say that. That angle is congruent to that angle. And so now this is ASA. This would be an ASA correspondence. ASA, and we have congruent triangles. We'll get that in a second. But don't forget, we need to say it. So we have, right, here's the side, here's the angle. We need to say the other angle. The other angle is angle YOQ, and that's congruent to angle XOS. And that's going to be vertical angles are congruent. Okay, and then step 6 is going to be the, not the very last thing. We have 2 more steps on top of that. So, right, we're just thinking back. What have we said? What do we need to say? I did all this work. Okay, so this came in from the given diagram here. That's not why I'm doing these arrows. You don't need to do this. It's hopefully not too confusing here. Okay, vertical angles are congruent. I spotted that from the diagram itself. So I have the ASA. We got to say ASA right now. We got to say this. So we got to say triangle YOQ is congruent to triangle XOS. And that's by the ASA postulate from chapter 3, okay? If we spot that we have those, we know those parts of a triangle, those corresponding parts of a triangle congruent in ASA correspondence, we know, right? By that postulate we have, we know the whole triangles need to be, this needs to be the same exact triangle as that one. They're just kind of mirror images of one another and in different places, but they're the same triangles. They have the same, all parts will be congruent because we just said that they're congruent. They're an ASA correspondence, okay? So there we go. And then what do we have? Last thing we need to say, we need to say that OX, right, which is right here, is congruent to OY, and they are. Look at that. YO, XO, or OY, OX. These are corresponding parts. They're in the same place of this in the two triangles. These are corresponding parts right here. Segment OX, segment OY are corresponding parts of, well, we have here congruent triangles, right? Congruent triangles. And again, this one I'm doing in color, you don't really need to do. So we can say as our last step that segment OX is congruent to segment OY because they're corresponding parts of congruent triangles, okay? You got some congruent triangles. We know for sure. I've proven that I have congruent triangles. Perfect. I can totally be certain that any of the corresponding parts would have to be congruent to one another. And that wraps up your puzzle, right? Proofs are just puzzles. That's what they are. And you got to string them together and do your best to connect all pieces of the puzzle together. But we fit it together. It feels good, right? A quote that I like here is from Edward Norton, who's an actor, right? Not really that relevant, but he made a movie, right? He made a movie because he'd been thinking about the movie for about 20 years. And his quote was, I was reading this book, it was a magazine article with him. He said, an unfinished puzzle just makes my head hurt. An unfinished puzzle just makes my head hurt. So now that you've gotten done to this and you've finished this puzzle, hopefully you can take a little breather and your head doesn't hurt too much. Okay, because I know these proofs sometimes, if you can't figure out how they work, they can make your head hurt. And then you're stuck doing the Jamboard and maybe your head's hurt until the Jamboard or beyond that here, okay? So if we think about this as being, so this is done, we're done here, but remember, build on itself. This was the only one we needed to get. We got this one from the given diagram, right? We can spot. Remember, there are some things we can get from a given diagram. We can use the angle addition postulate to say the measurement of one angle plus another angle equals the measure of the angles that they make up, the large angle. We use the segment addition postulate, and then we can use the vertical angles are congruent. Okay, we got that from the given diagram. Here we got this from the three things beforehand, the ASA, and then finally, the last step was, since we knew that triangles were congruent, we can say their corresponding parts are congruent. Okay, so chain of reasoning, we got another proof down, and I think the only other one you have on tonight's homework is number 20. Okay, and this one I think is a pretty quick one. I think this is just like transitive property, angle B, convert to angle E. You'll get that one pretty easily. Good luck on that. I will see you guys on Wednesday. And reach out if you have any more questions about the problem set you have. Bye.